This is Jeff Mucci with RCR Wireless News. Today we have Anritsu as our guest on our webinar, and today's topic will be titled Tracking Generator Applications for RF and Microwave. Before we get started, there are a couple of housekeeping items I'd like to bring to everyone's attention. Firstly, please do submit questions during the presentation, which will last about 45 minutes, and then we'll move into a Q&A session for 15 minutes. The questions coming in during the presentation do help the presenters weave some of the questions into the overall presentation. Secondly, links to this recorded webinar will be provided within 24 hours after the conclusion of the webinar. For actual copies of the PowerPoint, you'll need to contact Anritsu directly. So at this time, before we move into the actual presentation, we'd like to put a poll up for audience consideration. This gives us a better feel for the areas of interest and familiarity of the audience with today's topic. So if you could, take a minute to launch the poll or actually to vote on the poll we just launched. Today's topic is, or question is, do you have any prior experience using tracking generators? Simple yes or no question. We'll leave this up for about 30 or 45 seconds, or once we receive about 70% of the attendees voting. That didn't take long. We just exceeded about 70%, and we still have people joining the webinar, so I'm going to wait just a few minutes, Steve, if that's okay with you, or just wait another minute, because we are seeing people continue to join the webinar. All right, I'm going to close the poll in 5 seconds. If you haven't voted, please take a minute to vote. Okay, at this point, I'm going to close the poll and share results with the audience. About a dead even heat, Steve. 54% say yes, they have prior experience, 46% no.
Pretty well balanced.
Yeah. So at this time, I am going to hide the results and turn the presentation over to Steve Thomas, who's Senior Product Manager for Anritsu. Steve, thanks for joining us today.
Happy to be here. I think this is going to be a lively session. What I'm hoping is that it will be fairly interactive, with you asking questions to either clarify points or get coverage or something that we haven't talked about yet. Eric Wilkinson is here with me. He is going to be reading the questions initially and picking out the ones that are high priority to get answered. And he's an expert on this product, so he may actually answer some of the questions himself. Without any further ado, here we go. If I can just get the thing to go to the next page. There we go. Now, first the question is, what is a tracking generator? For the 54% who used them, you probably know. But fundamental features of a tracking generator: it's an unmodulated signal source. There are other sorts of generators you can have in an instrument that are modulated. Those aren't called tracking generators. In general, it tunes synchronously with the frequency of the spectrum analyzer. What that means is the tracking generator and the spectrum analyzer are always at the same frequency. It delivers leveled and calibrated output power over a fairly significant range. In this case, we specify for our products a power range of 0 to minus 40 dBm with some overrange capability. Some tracking generators have the capability to generate a fixed frequency CW signal. And near the end of the presentation, I'll give you some ideas of what you might use those for. Now, what are you going to use a tracking generator for? Basically to measure two-port connectorized devices. Attenuators, cables, filters, amplifiers, pairs of antennas. You can also measure the return loss of one-port devices, or device that can be terminated and turned into a one-port device. Attenuators, cables, that sort of thing. tracking generators are not useful for measuring frequency conversion devices because they change the frequency of the output, and since we're tuned synchronously, we won't see the output of the mixer because what we will see is the input frequency. If you want to use it to measure LO leakage through a mixer, it would work for that, but in general, it's not a good thing to use it for. Now, a general assumption, if you're going to measure cables or other low-loss devices, is that you can connect the spectrum analyzer input and the tracking generator output to both ends of the device under test without excessively long cables in between. I'll talk about another method for measuring long cables that's pretty handy, a little slower, but it works well. Now, when you're measuring low-loss devices, one of the most important things is accuracy of the measurement. The spectrum analyzer has a certain accuracy specification, and the tracking generator output has a certain flatness and accuracy specification. And those can be on the order of half a dB or more. So when you're making such measurements, you want to remove those inaccuracies from the measured result. And that's done using normalization. So what you're going to do in normalization is use the instrument to measure itself, and assuming the results are not noisy, once you've measured the measurement system, you can subtract those inaccuracies out of the final results and get a good, accurate result, more accurate actually than the accuracy of the instrument, because you're subtracting out the accuracy of the instrument. Okay, now, when you're doing normalization, what you want to do is create a signal path between the tracking generator and the spectrum analyzer without the device under test installed. That would include all the cables, adapters, amplifiers, anything else you have in the path, so they can be measured for normalization. Now, the ideal situation for measuring to do a normalization is where the device under test has one male and one female connector of the same type. To do that, you can just disconnect it from the system and connect the cable at one end, the cable at the other, to the two cables, and then you have an accurate representation of the loss of the measurement system, or the gain if there's an amplifier in there. And then there won't be any inaccuracies caused by adapters that are included in one place but not in the other. We'll talk about that in a little more detail in a moment. So if you have a device, these are fairly common devices that have two female connectors, you want to use two adapters that have the same loss. And later on in the presentation, I've listed some companies that make such adapters. And you'll use one of the adapters while you're doing the calibration in order to be able to connect the input and output together. And we'll use another adapter that has different connectors. In this example, you have a male and female adapter for the calibration, and then for the measurement, you want to use one that has two male connectors of the same loss, and then that adapter is taken into account during normalization. I think I beat that horse pretty thoroughly. So, hook up everything but the device to be tested, and then you do the normalization. So when you're normalizing, there's a single button press, and it says, on this particular instrument I'm showing, there's a normalize off on, and you'll see that on the one on the left where it says normalize transmission in progress, normalization is off. And when it's done, it'll say normalize on. Now, when I took this screenshot, you see a couple of things. There's a bright trace right in the middle of the screen on the left side that's at 0 dB. That was a partial measurement, and I wanted to get the picture with the normalized transmission complete still on the screen, but hadn't finished a complete sweep when I took the picture, because that goes away before the sweep's over. Anyway, there you have it. And so now, when you want to connect for measurements, you insert the device, and then the adapter, as we previously talked about, to allow you to make the measurements, and then you get, let me see, get the right place. Then you can get measurements such as this, where we've got, let me point to the top of the screen on the left. There's a little caret by 0.0 dB. That is the reference, the 0 dB reference. On the upper right-hand side is telling 0.0 dBm, and then doing measurements. All these are relative measurements. The big marker at the bottom, the display, shows that we're getting 110.8 dB of change from the marker 1 position, which is at the peak of the bandpass, to 130.5 megahertz away. So if I was doing just this measurement, I probably wouldn't bother with normalization, but because I'm making big measurements, big values, versus if I wanted to look at the bandpass area where I might have losses in the order of tenths to a couple of dB, that's when the normalization is really critical to get accurate answers. Now, in the instruments that I'm showing slides from today, we've done a number of improvements to the tracking generator. We've added some offsets. We've added a dB per division scaling that's independent of the spectrum analyzer scaling. And we've added the ability to do trace math on a tracking generator measurement. Pretty handy if you want to compare two devices. Now the little red circle is the reference point that I talked about earlier, and the red oval on the right-hand side is where you can see the scaling, 10 dB per division in this case. With a reference position of 10, that means at the top of the screen. The default, after you finish calibration, is at 5, which puts the reference position at the middle of the screen. So if you were measuring something with gain, you wouldn't want to have the reference position at the top. You wanted to have it someplace else. And you can move that to any one of those lines. Now, what if you need to measure a long cable? And by long, I mean one where it's long enough you can't readily get to both ends. I had this come up when I was doing some measurements with BART, the Bay Area Rapid Transit System. And the cable was quite long, and getting to both ends with one piece of equipment was just unreasonable. So what you do is you use two instruments. One has a tracking generator. You set that up at one end of the cable. And the other is just a spectrum analyzer. And you have it sweeping over the same frequency range as the tracking generator. You make the tracking generator sweep slowly, and then the spectrum analyzer sweeps quickly. And what you end up doing is painting on the spectrum analyzer the measured result over that frequency range. And it's pretty handy. And you can measure things as long as you want that way. It could be kilometers long. So if you're going to do such a measurement and you want it calibrated, you use max hold on the spectrum, the measuring spectrum analyzer to get the output signal captured. Slowly fill in as the tracking generator sweeps. And once the sweep is complete, you save that sweep into trace B on the receiving spectrum analyzer. And then you set up trace math to display trace A minus trace B, and that will give you when you hook up the cable for measurement, that will give you the loss of the cable without any of the other losses in the system. So you have one trace C, that shows you the actual answer of what you're trying to measure. Now, when you're measuring a filter, still all the processes are still roughly the same. Connect the filter between the tracking generator output, the spectrum analyzer input, and then adjust the center frequency and span so you're covering the range of the filter. So you do all of that to get the frequency range right before you do normalization. We'll set the output power to 0 dBm. That's not a required statement, but it makes it easy to read insertion loss before you normalize without having to do any kind of mental mathematics. Look at the dynamic range of the measurement and see if you have enough for the measurement you need to make. If you need more than measurement range than you're seeing with the default settings for the instrument, narrow the resolution bandwidth until you can see down far enough. One nice little trick is to narrow the video bandwidth so you see a cleaner trace, and it'll clean up the stop band area more quickly than if you had a wide video bandwidth. Now, to normalize or not to normalize, if all you really want to measure is the stop band isolation, you don't really need to normalize. Your inaccuracies are going to be small compared to the values you're probably going to measure. But if you're measuring in the passband, you need to normalize. Otherwise, you could have errors that are as large as the insertion loss you're attempting to measure. Now here are some pictures. I just left something in here that I shouldn't have. I chose some example resolution bandwidths, and you can see how far down you can see. In the upper on the left-hand corner, there's a 3 meg bandwidth or resolution bandwidth. You see down about 50 dB or so. But then, as you narrow the resolution bandwidth, you can see further and further down. Now that's at the cost of slower sweeps. But if you really need to see down, you can make it really narrow. In this case, I was using a 1 hertz resolution bandwidth to make the measurement. And the measurement was slow, 20 minutes or so. But if I need to see that far down, that's what I need to do. And the instrument at 1 gigahertz is capable of measuring about 120 dB down with narrow bandwidths. But you can get 100 dB down pretty easily in just a few seconds. The tracking generators we offer go up to 20 gigahertz, and up at 20, we're limited to about 80 dB isolation measurements because of the, 80 dB down measurements because of the isolation between the input and the output. One measurement that people like to do, and this is pretty common on cellular towers, is to measure sector-to-sector isolation. This is, in a lot of ways, very similar to a filter measurement, except you're not going to have a passband area. You calibrate if you want to. You probably don't need to because you're going to be measuring way down. And then, with the tracking generator connected to the antenna on one sector of a cell tower, and the spectrum analyzer connected to another sector that want to measure isolation between the two, you just let it measure, and you can directly read the isolation. Land Mobile needs to do this as well because they'll use cavities or separate antennas because they're transmitting and receiving on the same, or actually nearby frequencies. Isolations greater than 80 dB are typically desired so the repeater doesn't desensitize itself with too much signal hitting the receiver from the transmitter. One big problem that cell phone companies are facing every day is improperly installed cell phone boosters. The general rule of thumb is you need to have at least 60 dB of isolation between the inside and outside antennas if you have a booster that has 40 dB gain, and greater than 80 dB if you have 60 dB gain. Now, if you don't have that much isolation, what frequently can happen is what's supposed to be the outside antenna will transmit a signal that will be received by the inside antenna, and they'll get into what's called a fatal embrace, where one is talking to the other, and that creates a situation where the booster is transmitting at its maximum power for a short period of time. Then it says, "Oh my, I'm oscillating," and it turns itself off. But if the user is still talking on a cell phone, after a little while the booster will reset itself, try again, create another pulse, and each one of those pulses is at max power and will generally serve to take out a sector of a cell site, cause lots of trouble for other users. And, people are lazy. They may read the instructions that say the antenna needs to be outside, well away from the antenna that's inside, but they're in an office building in the middle of a high-rise, so they say, well, I'll just put it by the window, and I'll put the other one at the other side of the room. Not going to cut it. I've seen at least 2 instances of that where companies had to go, in one case, threaten to get the FCC involved to get the user to shut down the booster. So by measuring the isolation, you can know as you do an installation that it's clean, and you're not going to cause trouble for yourself or the cell phone network. When you're measuring antennas, you may very well receive over-the-air signals. There are a couple things to keep in mind. One, since you will be transmitting with the tracking generator over an antenna, there is the possibility of interfering with somebody's communication system. So what you want to do is keep the testing time short and keep the sweep time fairly fast, but generally a little slower than auto. And There's two considerations on power output. If you can use lower output power from the tracking generator, that will reduce the possibility of harmful interference. However, using higher power reduces the effect of external interference on the measurement. So I'm sort of waving my hand here as I'm talking. It's sort of a trade-off as to how good your measurement needs to be versus the possibility of causing interference. And it's a trade. There's no single right answer in this case. When people are doing this sort of measurement on broadcast towers, they'll actually put an amplifier, a 20 watt or 30 watt or even higher amplifier at the output of the tracking generator, and then a hefty input attenuator on the other side to reduce the power back down, and that will reduce the received interference by quite a bit, 30, 40, 50 dB, so they can make a much better measurement. They amplify it so they can attenuate it, and the attenuation attenuates the interference. Antenna aiming is another thing that can be used with the tracking generator for. There are other ways to do it, but it's similar to a measurement with a long cable. You put the spectrum analyzer on the distant antenna, the tracking generator on the nearby antenna. Could do it the other way around, but we're going to do it this way. And what you want to do is adjust the aiming of both antennas to maximize the received signal strength, basically to minimize the effective path loss by having the antennas aim directly at each other. Now, you do need a communication channel to coordinate measurements. If a LAN connection is available at both ends of the path, you could use Anritsu's remote access tool, which is shipped with our spectrum analyzers, to be used for coordination, because that way the operator on the tracking generator end can see the screen on the instrument at the other end, and it makes it a lot easier to get the aiming done properly rather than trying to talk through it with somebody. Yeah, a little to the right, no, a little more, no, go back, you know. You can see it yourself, that's just a lot easier. Now, you can also use a tracking generator to measure antenna patterns. This requires a little labor at the end. This is typically done in zero span, so you have a CW signal going out of the tracking generator. And what you want to do is set the instrument's sweep time to match the antenna rotation time. Now, I've done this sort of faking it just by hand waving the antennas, and it sort of works. But if you can simultaneously start the antenna rotating and start the sweep, at the end of the sweep, you've gotten the antenna around 360 degrees, save the measurement, and then manually plot the amplitude, received amplitude on a polar plot, and you will get an antenna pattern measure. So you can see the pattern of the antenna. Works pretty well. This is really sort of the poor man's version of it. There's some really fancier versions that use lots of software and external computers and all that. But here you're doing it with just the instrument. Now, another interesting thing you can do is measure one-port devices. And what you need to do this is a bridge, which is a component that when the signal goes into the in port of the bridge, it goes out the test port, and then signals coming back into the test port go to the out port of the bridge. So if we put a short on the test port, we get 100% reflection, and we do a sweep, and what we're going to be measuring during the sweep is 0 dB return loss. So this is 100% reflection, and that will give us our calibration point. Once you have the normalization done, and this is done just like any other normalization, you would then replace the device under test, or excuse me, replace the short with the device under test, and then what you will measure on the screen is the return loss of that device. You can use a tracking generator to measure preamplifiers. There's lots of things you can do here, but this one's just a basic measurement where we have an input attenuator to reduce the input power to the preamplifier enough so you're not saturating it, so you make it an accurate measurement. And during normalization, you take the preamp out of the circuit and connect the RF input to the output of the input attenuator. And so all that's taken into account during the normalization. Now, you may very well need the matched adapters, as we talked about earlier, to do the normalization and the measurement. This way you can measure the gain of the preamplifier. If you're interested in measuring the saturation, so 1 dB compression point of the amplifier, you could slowly increase the output of the tracking generator while watching the gain of the preamplifier until you start to get compression. And because the tracking generator output's fairly flat over let's see, several megahertz or 100 megahertz frequency range, this will give you a pretty credible measurement of the 1 dB gain compression of a preamplifier. You can fancy it up a lot, but for simple measurements, this is probably good enough. Now, let's say you want to measure a power amplifier. It looks very much the same, but with it, you add an output attenuator because the power output of the amplifier is probably greater than the power, the safe input of the spectrum analyzer. It can handle up to a watt. Let's say you have a 10-watt power amp. You want to add enough attenuation that you're not going to risk breaking your spectrum analyzer during the course of the measurement. Now, there are some adjustments that you can enter into in the tracking generator menu to account for those attenuators, to measure so you can measure the transmission or enter the transmission offset. So what you're measuring is directly the law or the gain of the amplifier without having to worry about the attenuators. And you would calibrate with all this stuff in place. Now, if you have a huge amount of attenuation, this may very well limit the dynamic range of the measurement. But since you're probably not measuring an amplifier whose output varies by lots and lots of dB, limited dynamic range is not a huge issue. Now, our spectrum analyzer tracking generator options have the capability of, in addition to tracking, allows you to select a CW output from the tracking generator that will stay at one frequency while the spectrum analyzer is sweeping. I think the uses of this are limited only by your imagination. You could use the CW output to measure gain compression. You could put it into, let's say, an amplifier to look at harmonics. You could look at it to look at image products or things that are frequencies that shouldn't be there, that should have been filtered out, that weren't quite in some sort of mixing process. You can use it as a local oscillator. You might need an amplifier in some applications there, but at lower frequencies, our tracking generators are spec'd to 0 dBm, but they can often deliver plus 10 or plus 15 dBm, which is sufficient to drive most mixers. We offer tracking generators right now in 4 products. The MS2720T is our most recent offering. And we have 3 different tracking generator options that match 3 frequency options. We have a 9 gigahertz option for the spectrum analyzer and a 9 gigahertz tracking generator. We have a 13 gigahertz tracking generator that goes with the 13 gigahertz instrument, and a 20 gigahertz tracking generator that goes with the 20 gigahertz instrument. One we've sold for several years is the MS2721B. It has a tracking generator option that goes from 100 kilohertz to 7.1 gigahertz. There are way over 1,000 of those instruments with tracking generators out in the field, so it's likely you're going to run across one at one time or another. They work a little bit differently than what we've been talking about today, but the concepts are all the same. And the MS2712E and MS2713E also have tracking generator options that work very much like what we've talked about today. Now, I think we've come to the time when we're going to look at the questions we've gotten and see if we've gotten some that are particularly good. Eric, what do we have?
Okay, Steve, a couple, I'm sorry.
Okay,
Steve, can you hear me okay?
Hear you okay, go ahead.
Okay, before we jump into the questions, a couple of housekeeping items. Steve, if someone wanted a copy of the PowerPoint presentation, should they contact you or should they contact somebody else?
They should contact me. You can send an email to my email address, which is steve.thomas@anritsu.com, and I will attach the PowerPoint and send it back to you.
That's great. And before we get into the actual questions and answers, I would like to launch another poll, and I'll leave this open for maybe 60 seconds. The question on the board is, what sort of devices do you want to measure a tracking generator? So I'll leave that open for, like I said, 45 to 60 seconds. We'll try to get to 70% or so votes. And Steve, while we're doing this, just if you don't mind, maybe you and Eric can look over the questions and flag the ones you want to make sure we cover. And I've got a couple of them that have already come in I want to make sure and ask.
Okay.
Okay, we'll leave this open for just a few seconds longer. If you haven't cast your vote, please take a minute to make your selection. Looks like filters is coming on strong, Steve. I don't know if that's a surprise to you or is that what you expected?
That's pretty well what I expected.
Okay. Okay. I'm going to go ahead and close the vote in 5 seconds. If you haven't voted, please do so. 5, 4, 3, 2, 1. All right, and I'll share those results. Steve, do you see anything there that surprises you?
Actually, I'm a little surprised that the cable measurements are as high as they are. I suspect almost everybody will end up measuring multiple things, but it looks like filters predominate.
Okay. So let's move into Q&A, and Steve, could you go over the power range of the tracking generator and the frequency range of the tracking generator?
Sure thing. We have a specified power range of 0 to minus 40 dBm with over and under power capability. If you ask for, let's say, plus 10 dBm, and the tracking generator can do it, it will do it. Otherwise, it will put an unleveled indication on the screen. The frequency range of the 3 options of tracking generators are 100 kilohertz to 9 gigahertz, 100 kilohertz to 13 gigahertz, and 100 kilohertz to 20 gigahertz. At the lower frequencies, let's say below a gigahertz or 2, you can get considerably more power. When you get up into the 18 to 20 range, you might be able to get plus 3 or 4 dBm at the high end. And generally, you can go down to about minus 50 dBm at the low end, so the spec value is minus 40.
Okay, and this is a message from the group, and it ties into that same question. If you don't mind, go over the dynamic range of the tracking generator versus a transmission management option versus the VNA for antenna isolation measurement.
Okay, we can do that. With a VNA, you have a relatively wideband measurement, and so getting, let's say, 100 dB down is tough to do with a VNA. But with a tracking generator, because you can change the resolution bandwidth, you can get dynamic range up to 120 dB at lower frequencies, 80 dB around 20 gigahertz. And for most filters and antenna isolation measurements, that is more than adequate. They beat a VNA by 40 to 60 dB. You know, VNAs certainly have their places if you need to get vector measurements. They're products for a slightly different purpose.
Okay, and which of those has enough dynamic range for repeaters with up to 90 dB gain?
Actually, the tracking generator and spectrum analyzer will allow you to do a 90 dB measurement for a repeater. VNA would have a hard time with that.
Okay. And how does the frequency range of the tracking generator compare to your spectrum analyzer?
That's a good question. I've actually been asked that numerous times. If you have a 9 gigahertz spectrum analyzer, you order the 9 gigahertz tracking generator. They're designed to match. 13 gigahertz spectrum analyzer, you order the 13 gigahertz tracking generator. And then the 20, you order the 20. You cannot order the 9 gigahertz tracking generator, for example, with the 20 gigahertz instrument. It's just not designed to go that way. The question does come up, since we have spectrum analyzers that go up to 43 gigahertz, why we don't have 32 and 43 gig tracking generators. It turns out the space to generate the 32 and 43 gigahertz signals or measurements is same space where the tracking generator goes in the lower frequency models. There just isn't room to put it in.
Mm-hmm. Okay, another question came in from Joe. The difference between tracking gen and sweep gen.
Well, functionally, they do about the same thing, but a sweep generator generally isn't tied in to a spectrum analyzer. So, if you were just looking at the signal out of the tracking generator, independent of the spectrum analyzer, you really couldn't tell the difference between the output of a sweep generator and the output of a tracking generator. It's only when you look at it and say, oh, that's part of a spectrum analyzer system, and the spectrum analyzer is at the same frequency, that the difference is apparent.
Okay, and next question, somebody asked about getting certified on these tools. Can you maybe talk about where they get certified and how they get certified?
That's a good question. At this point, we don't have tracking generator certification training. We do have cable and antenna analyzer training that Anritsu offers, and it's taught all over the country, actually around the world. And so you can contact 1-800-ANRITSU to get information on getting certified. I noticed just the other day that one of our distributors, Tally, is doing lots and lots of line sweep certification training classes. So you could also even go to Tally's website and see if they have one that's convenient to you.
Okay. And we have a question here that came in. I'm not quite sure how to phrase. Actually, there's two of them I'm not quite sure how to phrase. One refers back to your slide that had some offsets. Maybe you can talk a little bit more about those offsets.
Okay. Actually, I'm going to have Eric talk about the offsets because he's an expert on those. Here comes Eric Wilkinson to talk.
Okay. Can you go back to slide 10, Steve?
Slide 10, yes, I can. I think I can. There you go.
Okay, you notice the the graphic on the bottom, and there are three different adjustments to the power levels: transmission offset, reference level offset, and external gain loss. Those are for dealing with attenuators that are put in the test setup to correct for things like mismatch or a very high gain device that needs an attenuator to go with it. And then by entering those values, the numbers on the instrument screen show up the value at the DUT rather than the value the instrument is using. So for example, if you do generator external gain loss and you put a 10 dB pad on the output, when you set the instrument power level to say minus 10 dBm, that's minus 10 dBm at the output of the attenuator. The instrument itself would be putting out 0 dBm.
Thank you, Eric.
Okay, and another question, I'm not quite sure how to phrase it, talks about can these devices be used for testing Cat5, Cat6 coax for troubleshooting?
Well, Cat5 and Cat6 are not coax. I guess technically the answer is yes, but the challenge is going to be creating an adapter to pair or ribbon cable. So I don't think it's the best thing to do. Could be done. Normalizing may be difficult. So this just, I've never actually done a Cat5 measure or a Cat6 measurement with a tracking generator. And I'd have to think about how to create an adapter to be able to hook up.
Okay, we got time for a couple more questions here. Next one is, how difficult or easy is it to print out the displays for record keeping?
Very simple. The instrument has multiple capabilities to save measurements. You can save measurements as a spectrum analyzer file and then use a piece of software that's shipped with the instrument called Master Software Tools to allow you to print out onto basically any Windows connected printer. You can also save the screen as a JPEG file and then copy that into your computer and embed it into whatever presentation or report. The screenshots that are in this presentation today, I did that way. We actually have an undocumented shortcut. If I press Shift, dot, plus, minus, one at a time, I can save whatever's on the screen as a JPEG. And that makes it really handy to document what you've done. If you see something that's odd that you want to record or something that's really good you want to record, you can do it that way. Or you can save it as a spectrum analyzer file.
Okay. And Eric, you can see that the remaining questions we have coming in. Do any of those, do you want to field any one of those open questions?
TDR? What's the question?
Will the unit do TDR?
Time domain reflectometry? No, it really doesn't. I'm trying to think if I can figure out a way to make it do that.
So our vector network analyzers can do frequency domain reflectometry by using a Fourier transform. Basically the same functionality as a TDR, showing disturbances as a function of time or distance. However, tracking generators don't have phase, so we can't do the Fourier transform.
Thank you, Eric. Well, many of the other questions tie back to questions that have already been asked. So at this time, do you see any other questions you want to address, Steve? Otherwise, we'll go ahead and wrap up for today.
Okay, I've got Eric looking right now. He can say, no, not really. So I think we're finished with the questions.
Okay. Well, again, within 24 hours after we wrap up today, all the attendees and people who register will get a link to a recorded webinar. If you want copies of the actual slide presentation, please contact Steve directly. His email is steve.thomas@anritsu.com. Is that right, Steve?
That's correct.
Okay. Any closing comments, Steve, before we wrap up today?
Well, thank you all for attending. I appreciate the rapid responses to the polls. I hope you found this to be as useful as I found it fun to do.
Great. Thank you, everyone, and thank you, audience, for joining us today.
The organizer has ended the session, and this call will be disconnected. Goodbye.
Your door closed.